Hello everyone and welcome to Physical Science. Today we're going to be talking about nuclear chemistry. Yay! Alright, here we go. So, let's talk about the different types of radioactive decay. So, radioactive decay is how atoms decompose. So what happens in a radioactive decay is the nucleus breaks down to produce one or more different elements or isotopes, aka isotopes. So isotopes are the ones that we talked about earlier on in the semester that have a varying mass than what you would expect. So the number of neutrons varies from what the original atom is. So if an atom is losing the neutrons, it becomes unstable. So unstable atoms are radioactive. So we call them radioactive isotopes or radioisotopes, which means the same thing. The bigger the atom, the heavier the isotope, the more unstable it is. Just like the larger something is, the more unstable, the harder it falls. Same thing. So the heavier an isotope, more equals more unstable. So large things like uranium. Uranium is a very, very large molecule with an atomic number of 92, an atomic mass of 238. So this is a very large thing. It will spontaneously decay and it will lose alpha particles, beta particles, and gamma rays. And we're going to talk about those different types of radiation. So the type of radiation, there are different types. The first type is an alpha particle. So alpha particles are when you result loss of a helium nucleus. So it will lose a helium. Remember He, this is our notation. Helium with an atomic mass right here of 4 and an atomic number of 2. So it is losing 2 protons and it has an atomic mass of 4 because 2 and 2. So the charge of the net loss will be a plus 2 and your mass will be 4 AMU because 2 protons and 2 neutrons are being ejected. These are the largest types of radiation. The second type of radiation is beta. If you are losing beta radiation, you are losing beta particles, you're losing electrons. So the radiation symbol is that of an electron with a -1 charge. So when you lose an electron, you are resulting in a minus charge, 1 charge being shot off. The mass is 1 over 1,837. It's approximately 0. So you're not really losing any mass. This one you are losing 4. This one you are not losing anything. And then the last one, which is our strongest, is our gamma radiation, which is by the Y. This is high energy photons. This is straight up light shooting straight up out. So the light packet is being lost and you will not see a change in charge and you will not see a change in mass because it is just energy being ejected, just high energy photons. So those are our 3 different types from largest down to smallest. So alpha particles, guys, when they are emitted, almost anything can stop an alpha particle because it's pretty much a helium. If it could stop a helium particle, it can stop an alpha particle. So you are not going to be bombarded by alpha rays. You would have to leave your mouth gaping open and inhaling it directly in. And then you're just inhaling helium particles, or helium atoms. So these are not very penetrating. They can be stopped by anything, including paper. Beta, so right, alpha, stopped by paper, or almost anything. Beta are your electrons. Those can actually go through paper, but will be stopped by wood and thicker substances. So stopped by wood and medium thickness substance. And then your last type is gamma radiation. Gamma, it's even green like the Incredible Hulk. Well, gamma radiation will penetrate everything except for very thick concrete and steel. So, or lead, excuse me. Lead, the reason why you wear lead vests when you are getting x-rays is to stop the radiation, the gamma radiation, from penetrating more than what you want. So stopped by concrete and lead. PB, straight up PB, not peanut butter, lead. All right, so nuclear equations. When you're looking at a nuclear equation, it is telling you what the substance starts off as and what it is being broken down into. So if you have a loss of a helium, we call that alpha decay. So if you start off with uranium-238, so its atomic mass is 238, its atomic number is 92, and it decomposes down into 234, which is now thallium, with an atomic number of 90, and a helium particle. Hey, notice that if you add 234 plus 4, it gives you back to the 238. So this is seriously just splitting it off. So if you're trying to figure out what is going to result after an alpha particle is decayed, you just subtract your 2, see, 2 plus 90 gives you 92, subtract 2 from your atomic number and it will tell you what's being released. And then you'll have your helium particle. So this is emitted an alpha particle. This is alpha decay. The second example is showing you beta radiation. So you start off with iodine, and its atomic mass is 131, its atomic number is 53, and it is turning into xenon with an atomic mass of 131, an atomic number of 54. So you have added on an electron being lost. So when you lose an electron, if you see anything resulting in a loss of an electron, this is beta decay. And then the last type is if you actually capture an electron. This is radiation again, but this is not decay, this is buildup. So if you had Ag, atomic number of 47, and atomic mass of 106, and then you add on an electron or a beta particle, you end up with still an atomic mass of 106. Notice the mass did not change because electrons don't weigh anything. And your atomic number is now 46. So this is a captured beta particle, or an electron. So you can either lose a beta, beta decay, or you can capture a beta. So here's a nuclear equation. If I'm trying to figure out what goes here, all I have to do is look at the atomic numbers and the atomic masses. So if I'm trying to figure out what X is, so I have N with an atomic mass of 14, and I have an atomic number of 7. If I am adding an atomic number of 2, an atomic mass of 4, so if I have that, I have a total of an atomic mass of 18, 7 plus 2, 7, 8, 9, atomic number of 9. So I have atomic mass of 18. This is my total mass going in. The law of conservation of matter states that whatever goes in has to come out. So I have to figure out what X is. So I see that I already have an atomic mass of 17 from this oxygen. So what does this one have to weigh? Well, I just look at this one, 18 goes in. If this weighs 17 and I need to make it 18 coming out, it would only be a 1. So then if it's an atomic mass of 1, I look up on my periodic table and I see the only element with an atomic mass of 1 is hydrogen. So X would be hydrogen. So if you're trying to figure out a nuclear equation and you're trying to figure out a variable like X, all you have to do is add up the mass of what goes in and figure out from what you already have what this needs to be to make the mass coming out equal to what the mass is coming in. So if this is 18, this has to be 18 over here. The only way to get 18 is for this one to be a 1. If I look on the periodic table, I see that that would be hydrogen. So let's talk about the different types of radiation and the difference between radioactive decay and building, like slamming things together to create different substances. So fission. Fission is splitting. You're splitting the nucleus into 2 or more smaller nuclei. So nuclear fission is splitting. It starts like a chain reaction. 1 turns into 2, 2 turns into 4, 4 turns into 8. So it is going to be a chain reaction. It doesn't just double as your time passes. It's going to double and then double again and then double again. So it will go up exponentially. So if you have a reaction occurring, you're going to have it split and split again and split again and split again. So that is fission. Fission is splitting. Fusion, on the other hand, is combining of two nuclei to form one nucleus of a larger mass. This is smashing atoms together to create one. So fusion. Fuse versus fission. Fusion is when you have two smaller particles, bam, bam, smashing together to make one larger particle. So fission, splitting, fission is splitting, fusion is to fuse together. So, nuclear powers, pros versus cons. So, power, pro versus con. Pro, nuclear power produces a lot of energy. That's good because we need lots of energy. We want to charge our phones and do all kinds of other things. Con, nuclear waste is hard to dispose of. That means that we don't really know what to do with it because it has a really long half-life. And we're going to talk more in depth about half-life later. But it has a long half-life. For right now, know that it is just the amount of time it is needed for that sample to decay into half. So this is how long it takes to break down. So half-life equals amount of time needed to decay, half. Amount of time needed for it to split. And if it takes a really long time, we don't know what to do with it. The waste sticks around for a very long time. I've said very long time a lot, haven't I? Okay. So that is our nuclear radiation, fission, splitting, and fusion. Everyone have a great day. Be ready with questions.